Welcome to this presentation about the future of quantum computing and communications. The main topic of it is quantum artificial intelligence. Before diving into this fascinating subject, let me introduce myself. My name is Alejandra Cuadros. I'm currently pursuing a master in computer science engineering. And joining me today is my colleague and partner, Akid.
My name is Akid Farooq and I'm pursuing my master's in embedded artificial intelligence and robotics.
Together, we're going to explore the intricate world of quantum artificial intelligence, and we're really excited to share our insights and discoveries with you today. In this presentation, we will cover contents like Introduction to QAI World, State of the Art, Challenges and Limitation, and the Future of QAI. Without further ado, let's begin our journey to the world of quantum AI.
So let's discuss the introduction of quantum artificial intelligence. It's simply the combination of quantum computing and the artificial intelligence technology. So simply, quantum computing is a type of computation that takes advantage of quantum mechanical phenomena or postulates to perform operations on data. And artificial intelligence is the science and engineering of making intelligent machines, especially intelligent computer programs. So in general, we can say QAI or quantum artificial intelligence is a use of quantum computing for the computation of machine learning algorithms or in general artificial intelligence. Okay, let's move to quantum computing or postulates. Quantum bits, unlike a normal computer bit that can be either 0 or 1, a quantum bit can be both at the same time using superposition principle. And then we have logic gates, like classical logic gates, but operate on qubits. Qubits can do complex operations taking advantage of superposition, and entanglement allows more powerful computations. And quantum classification, we can convert classical bits to quantum bits or vice versa. And then we have quantum registers. It's just a collection of bits, and they are really powerful because they can represent and process a large amount of classical data sets simultaneously due to superposition principle. So let's talk about the state of the art, and I can say the current applications. So it finds applications in so many fields, and it's difficult to define how many applications it would have in the future. So let me pen down some few of the applications. It's complex. It's used in complex system modeling. It's just a fundamental in traffic pattern recognition or pattern prediction. It could be used in weather forecasting, financial market analysis, and it simply uses less memory. We can use quantum AI, or we can use quantum computing in machine learning. It's used for process and analysis of large data sets more efficiently. It could be used in fraud detection in payment card industry. So together we can form quantum machine learning for the faster computation of machine learning algorithms. And the third one, we can use it in drug discovery. It can simulate molecular interactions at an unprecedented scale that could revolutionize the field of drug discovery. And the third and the fourth one that's really cool, cryptography. So the quantum algorithms could potentially break current systems, leading to the need for quantum resistant cryptography. So simply we can use quantum computing or quantum AI in cryptography. And in a similar way, it could increase the security of the systems or the encryption systems. That's really cool about this quantum computing. So let's discuss about the state of the art or the technological advances. It can be used in error correction. Quantum systems are prone to errors due to coherence and noise. So advanced correction techniques are crucial for practical use of quantum computers. So we need error correction for the use of the quantum computers in practical sense. Quantum supremacy, its ability to perform a calculation that is infeasible for a classical computer. So it can perform a faster and a parallel processing computing that was not possible for classical computers. In practical applications, we are still in experimental stage, so there's a lot to do in this field, like in quantum AI. It's a lot to do. Let's see what happens in the future. And scalability, it's like making quantum computers with more qubits. Atom computing is like, if we talk about atom computing, that has just 1080 qubits. IBM was the first last record holder with 433 qubits. That means a lot of difference between the atom computing and the IBM's first quantum computer. So that's the difference.
So we're going to talk about challenges and limitations of quantum AI. we start with the technical challenges, we have a lot of complexities, like for example, qubit stability and coherence, because as we know, maintaining them is a primary challenge, and environmental factors like temperature and like electromagnetic interference can easily disrupt the qubits. Also, we have error connections. These systems are more prone to errors than classical systems, so we need to develop efficient methods to solve this. Also, scalability is a problem. Adding more qubits that increases the system complexity, so it's going to be easy to maintain that. And finally, algorithm challenges. We need to develop algorithms that can effectively leverage quantum superposition and entanglement to solve these problems. It's a key technical challenge. After that, we have AI integration. As we know, we leverage AI to improve quantum computing and vice versa. This is a win-win situation. So here we have hybrid systems and data transfer and interface issues. So basically, it's something that we need to solve between both of them. Another challenge and limitation is resource requirement. As we know, this is substantial for the development of QAI. We have specialized physical infrastructures. We know that we require highly controlled environments, and this is to maintain the qubit stability. Also, energy consumption. The cooling system that we need can be energy intensive. Advanced material and components. We know that we require materials and components, often rare, expensive, and also challenging to manufacture. And finally, computational resources for simulation and testing. We're going to need a lot of classical computational resources for hardware and also software. And finally, we're going to talk about human resources, the skilled workforce. We need expertise in multiple complex domains. So these people need to have interdisciplinary knowledge. Professionals have to blend a lot of knowledge in quantum physics, computer science, and also AI. Training and education. There's a growing need to specialize education and training to prepare the next generation of quantum scientists and engineers. Collaboration across fields. We need to solve these challenges between physicists, computer scientists, engineers, and data scientists. And global talent pool. This is going to be challenging in terms of accessibility, the diversity, and inclusion of the field. Okay, let's talk about quantum AI. Let's just start with algorithm development. We have three main ones. The first one is quantum machine learning algorithms, and this one, if they use quantum properties, they could solve AI more efficiently, like in classification, clustering, and optimization. The second one is error correction and optimization. Designing resilient algorithms to errors is crucial. And also these algorithms need to be error correction and noise resistant. So these areas are right now in active research. And finally, we have algorithm complexity and performance. And we need to understand the complexity of this and also performance and benefits over classical counterparts. Also, this one is in plain research as everything that is related to quantum. Finally, let's not forget about the ethical considerations of quantum AI. About our privacy and data security, we need to develop ethical frameworks and regulations for data usage and protection that is going to be essential. Also, access and inequality, we have the risk of having a quantum divide. And these inequalities are going to lead in technological, economic, and military power in the world. Finally, we need to be responsible about researching and development because it can interfere with a lot of topics like cryptography and security, economic disparity, employment and skill gap, misuse in surveillance and cyber warfare, bias algorithm and decision making, intellectual property and research, and environmental impact. In summary, the future of quantum AI comes with exciting possibilities and formidable challenges. These transformative advancements are redefining technology and its impact in our world. The future is waiting to be shaped by our collective efforts and innovation in this dynamic field. As Dr. Michio Kaku said, quantum computers compute on parallel universes. That's why they are so powerful. If you want to learn more about quantum AI, you can check the references we use for the presentation.